Alright, in this session we're going to talk a little bit about indefinite integrals and integration by substitution. Now, an indefinite integral mechanically is not that much different than working with a definite integral. The only real difference in how it's written down is that an indefinite integral doesn't have upper and lower bounds on the integral. So, to recall, a definite integral looks something like this, with a fixed upper and lower bound on the expression. And this is something with a definite value. Given what your function is and what the upper and lower limits are, you could work this out to a number, flat out. Whereas an indefinite integral looks a lot the same. The only difference is that it doesn't have an upper and lower limit given to it. But what this represents is all antiderivatives of f of x. So this really is exactly what we were doing before when we would find the antiderivative of a function. We would anti-differentiate. Same as integration or indefinite integration. So, looking a little bit at evaluating these, the only real difference in how they're written out is instead of substituting in upper and lower limits to get a fixed definite value, we really just stick an integration constant on the end of it to give us a family of solutions. Jump into example 1 on page 336, and hopefully this sort of thing is starting to look a little bit familiar. Now we're given the phrase evaluate x squared minus sine x dx, although what we're really doing is writing out the family of solutions, or the family of antiderivatives. The antiderivative of x squared would have to have an x cubed in it, and to deal with the 3 that would come down if we reverse this and take the derivative, we'd have a 1/3. And the antiderivative of sine would have to be negative cosine, and since there's already a negative there, we end up with plus cos x and a constant of integration. And what this represents with that constant tacked on the end is all possible antiderivatives of x squared minus sine x, and that is the indefinite integral of x squared minus sine x. And I will note there are some generalized forms of integrals on page 337 of your textbook, which you could use for reference while you're doing the questions, but typically if I were to give tests or exams, that sort of thing, I wouldn't give you that table of information. Most of those are things that you should be able to sort of rationalize your way backwards through. For instance, they do give a form for what the antiderivative of x to the n should be, kind of going backwards through the power rule, but you should be able to work backwards to say that x squared's antiderivative should have an x cubed in it, and so on and so on. From there, just to talk a little bit about notation, and I'm going to do that through example 3 on page 338. And we are told to let f of x equal x cubed plus 1, u equal x squared. And then we're asked to work out the following indefinite integrals. Well, the first one is pretty straightforward. I'm really just have the integral of x cubed plus 1 dx, which would end up being 1/4 x to the 4th plus x plus a constant of integration. No big deal. B is going to work out in a similar sort of way. All they've done is switch the variable. Now, it's worth pointing out that f of u would be u cubed plus 1 du, and the antiderivative will be 1/4 u cubed plus u plus a constant. If you express that in terms of x, it would be 1/4 of x squared cubed plus x squared plus a constant, or 1/4 of x to the 6th plus x squared plus a constant. Now where you have to be careful is if the variable in your function is different than your variable of integration. So it's worth pointing out that that would be the same u cubed plus 1, but now it's with dx. In order to do my integration, this variable has to match with the variable of integration, at least to follow the rules that we've talked about up to this point. So I'm going to rewrite that in terms of u, where u is x, or rewrite in terms of x, since u is equal to x squared. This would be x to the 6th plus 1 dx, whose antiderivative would be 1/7 x to the 7th plus x plus a constant. So again, just to be careful that the variable that you have in your function matches up with the variable of integration. If it doesn't, you have to find some way to make it match. Alright, so the second part of this, and the one I'm going to do a few more examples on, is a specific technique to integrate functions that you might not immediately know how to integrate. And that is integration by substitution. And I'm just going to dive right in with some examples. I think your textbook refers to this as anti-differentiation by substitution, but they effectively mean the same thing. This is example 4 on page 338. We are asked to evaluate the integral, the indefinite integral, of sine x times e to the cos x dx, which looks like a big mess when you first look at it and think, how on earth am I going to find out what the antiderivative of that is? Now, if you're thinking about integration by substitution, what you're kind of trying to look for in your expression is a pair of things, one of which would be the derivative of the other. What jumps out to me in this case is cosine and sine. They are, in fact, one is a derivative of the other. So for a substitution, I'm going to let u equal cosine of x. Now you look at that and immediately you see this thing. It's like, oh, well, okay, I can do this. But this doesn't help me out a whole lot because it's just introduced some variable here that doesn't match up with my variable of integration. But then I'm going to go one step further. If I take the derivative of this thing, then I end up with derivative of cosine is negative sine. And restated, the differential du would be equal to negative sine x dx. And you might notice that I've got a sine x dx right here. I can think about this in two ways. I can either make this statement look like what I've got here, and sine x dx equals negative du, or I can rewrite this for dx and substitute into my expression and have things cancel out. Either way works. This is a little bit more elegant and doesn't introduce the possibility of having a division by 0 in a weird place. So if sine x dx is equivalent to negative du, then this expression is equivalent to the negative of e to the u du. Now that is much easier to deal with. The antiderivative of e to the u is just going to be e to the u. So I end up with negative e to the u plus a constant, and then I fill my substitution back in. Negative e to the cos x plus a constant, or, summarizing, the integral of sine x times e to the cos x dx is equivalent to negative e to the cos x plus a constant. And we're going to do a few more examples of this. Again, the important thing you're looking for is that pair of terms, one of which is the derivative of the other. Now, if you're following that through, you might have said, well, why didn't I let u equal sine x? I could have done so here, but the problem is that then, when I took the derivative, I would just have a cos x dx, not an e to the cos x dx. So I worked with what was in the exponent. Example 5 on page 339 asks us once again to evaluate x squared times root 5 plus 2x cubed dx. So again, you look for that pair of things, one of which could be the derivative of the other, or at least close to the derivative of the other. And I might notice that my variable in here is an x cubed, but outside I've got an x squared, which would be the derivative of that. So I'm going to try to let u equal 5 plus 2x cubed. If I do that, then du would equal 4x squared dx, or, if you like, a quarter of du would equal x squared dx. And x squared dx I've got right there. So substituting in, this becomes equivalent to the integral of 1/4 root u du. I can bring the 1/4 outside, rewrite the root u as u to the 1/2, and then think about what the antiderivative would look like. Antiderivative of u to the 1/2 would have to have a u to the 3/2 in it, and then if I were to go back the other way and take the derivative of this, I'd bring it 3/2 down, so I'd need a 2/3 to get rid of that. Or, in short form, the integral of x squared root 5 plus 2x cubed dx would equal, multiplying that through, 1/6 u to the 3/2 plus a constant, but I should put my substitution back in, and that would equal 1/6 of 5 plus 2x cubed to the 3/2 plus a constant. I have enough room here for example 6. And what I'm evaluating is the integral of cotangent 7x dx. Now, whenever you're dealing with just a cotangent or just a tangent inside your integral, it's usually a little bit easier to break it down into cosine and sine. Cosine 7x over sine 7x dx. Then you've got that cosine sine pair again, where one is close to the derivative of the other. If I let u equal sine of 7x, then du would be 7 cos 7x dx. Cos 7x dx, cos 7x dx. So I just have a factor of 1/7 that's in there. 1/7 du would equal cosine 7x dx. Substituting in, my expression becomes 1/7 of 1 over u du. Now the 1/7 is just a constant that will come out. You might recall the integral of 1 over u is ln u, although not just ln u, it's actually ln the absolute value of u, for an important reason. If you think about what 1 over x looks like. Y equals 1 over x. I'm not going to be able to sketch the whole thing out right here, but this little sawed-off thing like this. But its slope is always a negative decreasing number, or a negative number. It's always getting smaller as you go along. Ln is this number that's always negative, but it only exists for numbers greater than 1. So if I take the ln of the absolute value of x, it goes something like this. And if I think going from the derivative of ln absolute x to 1 over x, you'll see the derivatives at least roughly match up. Here, my derivatives should be negative numbers that are becoming more and more negative as I go along. But after this point, my derivatives should be positive numbers that keep getting smaller and smaller and smaller. So that's part of the reason why we end up with the absolute sign around u here. That becomes more important when we get into more definite integrals later on. So I end up at 1/7 ln of the absolute value of sine 7x plus a constant. A few more examples. Next is example 7 on page 340. I may or may not do each one of these, but I'll take a look at A. We've got the integral of dx over cos squared 2x. Remembering your trig identities would be helpful for this. You might recall that 1 over cosine is secant, so this is effectively the same as the integral of secant squared 2x dx. If I let u equal 2x, then du equals 2dx, or dx equals a half du. This becomes 1/2 integral secant squared u du. And if you recognize secant squared, because that's the derivative of tangent, so the antiderivative of secant squared is simply tangent. And this becomes 1/2 tan 2x plus a constant. And that one you might have been able to reason your way through. You know the antiderivative of secant squared should be tangent. And if you're working with 2x, the derivative of this would bring a 2 out, so you need a half to balance that. In B, do I want to do B? I'm a little bit more interested in C. I guess I'm going to jump to C. Integral cos cubed x dx. Now this is one that always tends to catch people up a little bit. But what you can do is you can break that cosine cubed up into a cosine squared times a cosine. And then the cosine squared you can rewrite, thanks to the Pythagorean trig identity, as 1 minus sine squared. And the whole point of doing that is that it ultimately lets me take all the trig out of this expression before I find the integral. If I let u equal sine x, then du is going to equal cos x dx, which is what I have right here. And then this expression becomes integral 1 minus u squared du, which is much easier to deal with than the trig stuff. The antiderivative here would be u minus the third u cubed plus a constant, and then I can just fill my substitution back in. sine x minus a third of sine cubed x plus a constant. All right. In examples 8 and 9, we're going to see an instance of using the substitution method to work through a definite integral. This is example 8 from page 341, where I'm asked to evaluate the integral from 0 to pi over 3 of tan x secant squared x dx. In this case, I should work out to a number at the end, since I'm going from 0 to pi. So I look to see if I can find that pair of term and its derivative involved, and the derivative of tangent is secant squared, so that suggests a substitution to let u equal tan x. In that case, du would equal secant squared x dx, which is exactly what I've got there, and my integral becomes u du. But it's important to note here, these limits of integration are based on the variable x, not on the variable u. So if my x value is 0, that means u equals tan 0, which is also going to be 0. But if my x value is pi over 3, the tangent of pi over 3 is equal to root 3. So that becomes my new upper limit of integration. When x is 0, u is 0. When x is pi over 3, u is root 3. So then I evaluate. The antiderivative of that is a half u squared. Try to integrate from 0 to root 3. And I end up with a half of root 3 squared minus a half of 0 squared, or 3 halves. One last example of that, example 9 from page 341, where we are asked to evaluate the integral from 0 to 1 of x over x squared minus 4. Again, I look for that combination, something that's derivative, and the derivative of x squared minus 4 will just have a linear component to it. Left my dx out. So I'm going to let u equal x squared minus 4. Then du would equal 2x dx, or a half of du would equal x dx, which is what I've got right there. So this then becomes an integral of, effectively, 1 over u du. But my limits of integration now, when x equals 0, u is going to equal negative 4. When x equals 1, u will equal negative 3. So those are my new limits of integration. Now the integral of 1 over u is ln u, ln of the absolute value of u. And you can see here, if we hadn't included those absolute value signs, I'd be trying to take the logarithm of negative numbers, which doesn't work out very well. This becomes 1 half the ln of the absolute value of negative 3 minus 1 half the ln of the absolute value of negative 4. Which would end up being, those of you following along at home, ln of 9/16. Nope, that's not correct at all. 1 half the ln of 3/4. Remember that I could factor a half out, and subtracting logarithms gives you the same result as dividing their arguments. So that's a few examples of trying this technique of substitution to work out integrals. There'll be some work along with this for practice in the Google Classroom, and that's all I have for now. All right, everybody. Thanks for listening.